Hi, everyone. Welcome to yet another edition of the talks in our seminar series. So maybe we'll just give it a second for all of you to settle in. Okay, all right. So today we have with us Professor Suresh Venkatasubramanian from University of Utah. We are very excited to have Suresh with us, and Suresh is going to talk about some of his latest work on explainability. But before we get into the details of Suresh's talk, just a few, quick logistical things. As you all know, the talk will happen from 12 p.m. to 1 p.m. So basically 12 to 12:45-ish is the talk, followed by 15 minutes of Q&A with Suresh about his journey and other aspects. Then 1 to 1:05 p.m. would be break. 1:05 to 1:30 would be participant-driven discussion on the same Zoom link, which will not be recorded or live stream. I just want to also point out that currently we are recording this talk and it's also being live streamed on YouTube. So if you don't want to appear in the recording, please exit Zoom and watch the YouTube live. But do join us again at 1 p.m., at which point we'll be stopping the recording. Okay. All right. So just a few words about us for those of you who are new here. So we are the Trustworthy ML Initiative. We basically sort of started this sometime last year, where several of us just organically came together and thought there is like a need for this kind of a community or a forum where all the folks and researchers and scientists and engineers working on this topic can come together, discuss their work, hang out, network, and so on. So that's how this came about. And we have the following goals and outreach efforts. So our goals are to basically provide easy access to fundamental resources in the field. To this end, we have a curated list of tutorials, courses, seminal papers on different topics under the Trustworthy ML umbrella. And our goal is also to provide a platform for early career researchers to showcase their work. As part of this, we have the Raising Star Spotlight Talks and also the Twitter highlights of up and coming researchers. We also want to facilitate discussion and debate in the community, for which we have an active Twitter forum. Please do check that out and keep sending your messages and tag us there. And of course, the broader goal is to basically build a community of researchers and practitioners, which we are trying to do through the seminar series, the participant-driven discussion after the seminar series, symposiums, workshops, and so on. And the agenda for today again is from 12 to 12:45 p.m. Suresh will be giving the talk, and Suresh has also kindly agreed to take questions through his talk. So he'll pause for questions periodically, and I can pick up some of the questions that you guys ask. So please don't forget to submit, upvote, and comment on the questions using the Zoom Q&A tool. From 12:45 to 1 p.m., there'll be again residual Q&A and moderated chat with Professor Suresh. So we'll talk about his research journey, his journey in ML, how he's excited about the topics that he's working on today, and the future of trustworthy ML broadly. We'll take a short break and we'll convene back for participant-driven discussion at 1:05 p.m. again, which will not be recorded. Okay. Okay, so with that said, let's get to today's talk, which is very exciting. So Suresh is going to talk about the limits of Shapley values as a method for explaining predictions of machine learning models. So before that, just a quick intro. Several of us in this community are already very well aware of Professor Suresh's work. He is a professor at the University of Utah. His research interests lie broadly these days in fairness and also more generally in the impact of autonomous automated decision-making systems in society. And Suresh is broadly interested in algorithms, computational geometry, data mining, and machine learning. He has won several awards, including the NSF Career Award, Test of Time Award at ICD 2017. So with that, I think I'll pause here and I'll let Suresh talk more about his research. Thank you so much for joining us again, Suresh, and over to you.
Thanks a lot, Hima, and thanks a lot to all of you at the Trustworthy ML Initiative for having me over. It's a pleasure, and it's a great group of people to talk to, so I'm glad I can do this. Let me So this talk is basically about Shapley values. It's about explanations, and it's about an attempt, I think, which is, at least odd for me because I'm a theoretician by training, to push back on sort of attempted theoretical formalisms trying to capture what explanations actually mean. So let me explain. Or well, since we're talking about explanation. So of course, XKCD has the definitive take on all explanation systems. And I'm pretty sure many of you have seen this before. And if you haven't, you can enjoy it for a minute too. So a lot of explanations is really about storing the pile of data, right? So how do we, the core question is, how do we understand what the output of a machine learning system? And there are many, many reasons for this. And I think that's also important to realize that there isn't just one reason that we want an explanation. There are reasons, for example, if you're debugging a system, you'd like to know why it's doing what it's doing, you may need to make some tweaks. There may be that you have to explain to your boss why the system is making certain predictions about company revenue or whatever, and then see with them. Maybe you're trying to find an explanation for the system because you're trying to intervene in some way and you want to know if your intervention is going to have any effect. Maybe you want an explanation because you're worried about something like bias, right, or discrimination of some kind, and you want to know if the system is using things it shouldn't be using. There are many, many different reasons why you might want an explanation of a system. And which means there are different ways in which you can express that explanation as well. And so I'll be talking about one specific mechanism for generating an explanation. And it's not the only one, but it's an interesting one that has received a lot of attention in recent years. So it seemed like one that worth studying. And this is sort of a one that's roughly speaking based on game theory. And so again, starting with the basic question of, why is the ML system making a decision? The conceit of this framework is to say, imagine that the features of the model are players. They're playing a game, and this game, the outcome of the game is the result of the model, right? And so what you want to do is try to understand how to assign contributions to players in the outcome. So if you think of players playing a game and there's some outcome, now you get some reward from the game and you want to distribute that reward in some equitable manner among the players, reflecting somehow their influence on the outcome. So now if you think of players as features and the outcome as the result, what you're saying is that, can we attribute a value to each feature that characterizes its influence on the outcome? So this is one kind of explanation, right? It's not the only kind, but it's one kind of explanation that says, I will try to explain my model by telling you the relative weights of different features in contributing to that outcome, either in general or in a specific prediction. And maybe if I say, oh, you didn't get the loan because, the feature that the reason why the system refused to give you a loan is because this feature, your prior credit history, had an undue weight. So you might think, okay, the system was influenced by my presumably bad credit history, and that's why I didn't get a loan. So that's the way in which the hope is that feature influence mechanisms give you an explanation. So how might one go about using game theory? Seems like an odd thing to do to understand feature influence. So here's the idea. And this goes back to a very old concept in what is called cooperative game theory. So where players are not playing against each other, but are trying to cooperate to come up with some successful outcome. And it brings up the idea of the Shapley value. I'm going to break my full screen mode for a second because I'm having some little bit of issues with the way my thing looks, but I will fix that in a second. Okay. So, so briefly speaking, Shapley values are things defined on a game, and I'll tell you what a game means. A game basically consists of players, so there could be D players in a game, and a value function that for each coalition of players, so it's a function from the power set of the players to R, gives you a value. That's the value in R. The idea is that the players might team up in different groups. If a particular coalition of players teams up, this is the value you get. So like there are 5 players in the game, 3 of them decide to work together and 2 of them slack off, then this is the value. Maybe 4 of them, a different set of 4 decide to work together and 1 person slacks off, that's the value. So you have a list of 2 to the D numbers that characterize what the value of each coalition is. And the grand coalition is when they all work together, okay? So in this game now, once you set up, so to specify the game, you need to specify the number of players and you specify the value function, which is these 2 to the D numbers. Once you have that, the game is well defined. And now you can start inquiring about the structures needed to estimate these influences of different players. So the first notion that's important here is what is the marginal contribution, right? So if I see a coalition forming, right? So there's some coalition of set S, and it has value V of S, and I show up and say, hey, I'll help you. So then we get the coalition S union I. How much value have I added to this? Well, this is a marginal contribution, right? It's a marginal contribution of me with respect to this coalition. Like if it's a different coalition, it might look different, right? But in this coalition, my marginal contribution is the difference between the value of the game before I showed up and after I showed up. So that's pretty certain, right? So then the Shapley value, which is this fairly complicated expression, which has a much more intuitive explanation, is something like this. Imagine, so we will rely on this visualization very heavily because we're talking about subsets of players. We can imagine that the game is really defined as a function on the hypercube. Namely, it's a d-dimensional hypercube. The binary encoding of every vertex on the hypercube corresponds to whether a player is there or not there, right? And so each node is one coalition, all the ones in that bit vector. And when you move on an edge, you're basically, if you're going towards more ones, you're adding a player, or maybe you're removing a player. And so the value function can be thought of as a scalar function on the hypercube. So once you have that in your head, you can say, well, there are many ways in which I as a player is the ith coordinate, right? So there's a sort of I minus one, d minus one dimensional hypercube consisting of all my contributions, right? And so any path from no one to the grand coalition will go through me at some point, and there are different paths. So the Shapley value basically says, over all possible ways of building the grand coalition, so all possible paths from 0 to the grand coalition, what is the average value of my contribution? Because again, remember, for different coalitions, I might have a different contribution. It's not, my contribution is not independent of the coalition. In fact, that's a very special case we'll get into in a second. So the Shapley value basically says, on average, over all possible ways of building the grand coalition, how much do I contribute to the proceedings? And this is a somewhat intuitive and somewhat, I like to think of it as a geometric way of thinking about the Shapley value. There's also an axiomatic way of thinking about it, which is where it comes from. And there are certain axioms that Shapley values uniquely satisfy. So once you set up some axioms you want your cooperative game to satisfy, so the properties to satisfy, then you get Shapley values out. And I won't go into them here, but they are sort of relevant in a game theoretic sense. Okay. So once you've defined Shapley values, you can now start exploring what it means. And so let me walk through an example of this just to get a sense of this. So this is a very classic game. It's called the glove game. So the glove game is as follows. There are players who want to sell gloves. Gloves are $1 each, but they must be sold in pairs. We need two gloves. So player A has 9 gloves, and therefore on her own, she could sell 8. Player B has 3 gloves, and on his own, he can sell 2. So the value of the game is the value of the gloves, the revenue, basically. So if they work together, they can sell 12 gloves, which corresponds to saying that in the 1, 1 node on the square, which is a 2-dimensional hypercube, the value of that is 12, right? If player A worked only by herself and player B just decided to take a break, then she can sell 8 gloves. So therefore, her value is 8. Similarly, if player B was working by himself, he can sell 2 gloves. And if no one did anything, they sell 0. That's pretty clear. So you can write out exactly this game, and you can sort of write out the values, and you can look at what the contributions are. And notice that in this case, it's kind of interesting is that, as I said, the marginal contribution of, say, player B, marked in blue here, is different depending on whether B is joining the empty coalition or whether B is joining A, right? If B is joining the empty coalition, the marginal contribution is 2. If B is joining the coalition from A, it's actually 4. And similarly for the contributions of A, it depends on which coalition she joins. And so now you can look at all the possible ways of going from 0 to AB, and then average out the contributions of B along those ways, right? So if you take the path going from the empty set down to B to AB, the contribution of B is 2. If you take the path going from the empty set to A to AB, the contribution is 4. The average is 3. Similarly for A, if you do the same thing, 10 plus 8 divided by 2, the average is 9. And so in this case, not surprisingly, the Shapley value of A is 9, which kind of makes sense because that's the value A has brought to the table with those 9 gloves. And the Shapley value of B is 3 because that's what B has brought to the table. And notice that this comes from a somewhat interesting interaction between them, because by themselves they couldn't have generated this much value. They would generate 8 and 2 by themselves. It's working together brings this, but now you have to apportion that value appropriately between them. Also note that 9 plus 3 is 12, and this is not by accident. The intention of the Shapley values is that the sum of the Shapley values should be the overall value of the grand coalition, because it's actually a division of the grand coalition value, which is the maximum value. So this is a very simple example. In general, computing Shapley values can get a lot more complicated. Not surprisingly, this is exponential number of players, and I can answer questions about that in a bit. There's also a lot of interesting work there as well. But this is the basic setup. And then you can say, well, okay, that's all well and good, but what does this have to do with machine learning? And that's where it becomes a bit more interesting. So this is based on an idea from a paper by Lundberg and Lee sort of a couple of years ago. The idea is the following. Suppose you want to define a game with respect to a model and an input. As I said, we'll think of players as the game, as the features of the model. We'll think of the grand coalition as the value of the function on the input, right? So the value function V with respect to a model and a particular variable is the evaluation of the function on a variable. Then the question becomes, what about other coalitions? If I need to specify a value function for every coalition to specify a game to run the Shapley value calculation, I need to know what other coalitions. And this is where you have to make some choices, right? So there are different ways you can think about doing this. There are basically various kinds of interventional processes to interpolate away from the function value itself. So for example, what is called a conditional distribution says that the value function on any subset of features S, right, corresponds to the expected value of the function over the input, where you condition the set of features that you fix on to be corresponding to the set of values in that input. So in other words, if my input Z has 10 variables, right, say 1 through 10, and my subset consists of 1, 2, then I fix the values 1 and 2 in my function and then average over everything else. And this is one way of doing this. That's why it's called a conditional distribution. Another way to do it there's a whole class of things called interventional distributions where you don't condition on this. You just sort of build, you fix the value and you average over the whole thing. Okay. Right. So that in other words, there are different choices for, and as we'll see, these different things have different implications. Okay. All right. Notice the difference between the first and the second is that in the first, if you have fixed the values of XS to be a ZS, that might change the overall distribution you average over, right? Because that might change the values in S bar, the complement. In the second case, you're just hardwiring those values in and you're ignoring anything else. So there's a subtle difference between them that is controlled by the ways in which interactions happen. And we'll get to this in a bit. So for example, here's a very, very simple example. I have a simple predictor f of x1, x2, which is equal to x1 plus x2 divided by 2. And I want to explain the predictor on input 1, 1, assuming variables that have been distributed independently with mean 0. You need to have that information because you're doing this expectation calculations. So then you can again build a game as I described on the hypercube, look at the different contributions, and not surprisingly, both variables, looking at the blue arrows and the red arrows, have the exact same influence, which is what you'd want. So one of the questions that has come up at least in recent times is, do Shapley value-based explanations do what we want? Do they truly capture what we need from an explanation system as opposed to, say, from a game theoretic system? And in this paper that we published last year at ICML, we kind of argued that they don't. And we tried to make this argument along 2 dimensions. One was, do they mathematically capture what we want from explanations? And more broadly, do they capture what, if we think of explanations as part of a broader socio-technical system, what people in that system would want? Right, so I'll briefly talk about that, about these parts, just to give you a sense. And I'll probably spend more time on the first part because that'll give me a jumping point to the second part of my talk. But maybe I should stop here. This may be a good point to stop, just to see if people have questions about Shapley values or about the conversion to explanations.
So far we don't see any, but
Okay.
everyone please keep your questions posted, and Suresh will be taking the questions through the talk. Okay.
Perfect. Very good. So let me continue. So as I said, the question at hand is, do Shapley values, or Shapley value-based explanations to be more precise, do they work as a model for doing explanations? One of the things that has come up, and I think this is a sort of, I'm going to make this as a broad point, but in our paper, we sort of lay this out in a couple of specific details, is that Shapley values are, remember, are designed to capture the influence of players in a game where the players act independently, but cooperate together, and the value function captures that cooperation, right? Otherwise, the players are assumed to be independent of each other. And this is one point we believe where this causes problems for using Shapley value-based systems for doing explanations. So let's look at this example here. So on the left side, we have a function of 3 variables where 2 of them are sort of probabilistically forced to be identical. So they only differ in a set of measure 0. Or if you want to be less precise, that basically the stochastically the same. On the right side, I just went ahead and determinized this by just saying, look, I'm going to substitute z equal to y. Now, I can ask now, what is the Shapley value of y, with respect to some particular input, and write down the expression for it. And you can write down the expression for what it's going to look like on the left side. You can write down the expression for what it's going to look like on the right side. And I've deliberately written this way just to show you that you can, without even substituting the values, you can see these 2 things are going to be different because they have different coefficients on these properties that are sort of independent of z. They're just a function of y and z, y and x. What this is basically an example of, and again, like I said, we have more of these examples and illustrations in the paper, is that because there's some kind of correlation or interaction, what you're going to get, so in this case, the failure is that both functions, the functions are going to return different estimates of the influence of y on the outcome. Whereas if you look at the 2 functions themselves, they are essentially the same thing. At least they seem like the same thing. They may be different in some specific way that is relevant to Shapley values, but from the point of view of explanations, they're the same thing. It doesn't really matter from the purpose of influence that in one case, y and z were sort of probabilistically identical, and in another case, they were deterministically identical. Okay, and so other examples that we have illustrate this point that any time there are interactions between variables, whether they're in the distributions or in the way the functions are set up, Shapley-based explanations seem to fail. And I think there are many reasons for this. And one of the questions that sort of led us to sort of figure this out, to try and understand what is going on, is to say, why is it that interactions seem to be causing Shapley-based explanations to fail to capture what we want from explanations? So this led us in sort of a couple of different directions, right? So, but mainly we had to understand is there a different way to think of the underlying mathematics behind what Shapley values are doing? Is there a way to translate the axiomatic framework it's based on into something that is more intelligible in our context? And what can we do about it? Okay, so that led us to the second piece of work that I'll talk about now, which was sort of presented in a workshop form at WHI last year, and is sort of being reviewed right now. And this is what we're going to call Shapley residues. Okay, so this actually led us on a very kind of interesting exploration through an alternate way of thinking about how Shapley values work. And the way I like to think of it is that most of the discourse around Shap and Shapley values relates to sort of a purely game theoretic notion of the world, right? What this does is bring in geometry, which makes me happy because I'm a geometer by training, but it brings in geometry in a very fundamental way and actually exposes us to a very different line of literature that focuses on the geometric interpretation of Shapley values, which I think is cool regardless of anything else. So let's talk about that for a bit. If you recall, I had mentioned a while back that it would be nice if the contribution of a player to a coalition did not depend on which coalition they were joining, right? That their contribution was independent of the coalition. It turns out that if you have a game where this happens for all players, it's a very special kind of game. It's called inessential. The name is a little, frankly, a little bit annoying, but it's basically a way to capturing it. It's a way of saying the game is trivial. That if a game is trivial if the value for any coalition can be expressed merely as the sum of the individual player contribution. So there's no interactions between them, right? So in essentiality, each player contributes into the value function. And not surprisingly, if you just crunch through the math and figure out what the Shapley value for any player is, the Shapley value for any player is exactly the value on itself, which again intuitively makes sense, right? Because if I'm saying the Shapley value is the average contribution of a pair along any path, and we're saying, look, it doesn't matter which path you take, the player gives us exact same value, then of course the average of a bunch of identical values is the value itself, which is V of I. So inessential games are kind of easy games. They're kind of the easy case for understanding influence, because if every player contributes independently, then you don't need to do anything. You just say, okay, what happens when I just use when player I works by itself? That's it, we're done. This is the easy case for understanding feature influence. And so one thing that would be nice, and people spent in the 80s a lot of time trying to explore, is could you think of the Shapley value as some kind of projection onto the space of inessential games? So the space of inessential games is a vector space. And so you could say, well, I have some game. I have the space of games that are nice. And maybe the Shapley value for this game corresponds to the Shapley value, which is easy to compute, for the inessential game that's closest, right? So you look at the game that's closest to this original game and look at its Shapley value for I, and that's the one you want. And so people spend a lot of time thinking about whether this might be possible. And it turns out it's not true, unfortunately. It would be very nice if it were, but it's not true. That doesn't come from a natural sort of orthogonal projection. It's a bit more, it's much more complicated than that. But that intuition, right, of somehow that the Shapley value comes from finding a projection onto a nicer space and then reading off values from there, turns out to be a useful projection. It's a bit more involved in this. So to that, I need to do a little bit more work. And to that, I need to define the derivative of a game. Okay. So what's the derivative of a game? Well, it's what you'd expect, the discrete derivative of a game. Basically, if you have a hypercube and you have a scalar function defined on the vertices of a hypercube, then I can define a derivative on the edges of the hypercube, right? Where each edge corresponds to, and this is a directed note, the value on the edge is the value on the sort of bigger side of the edge, S union I, minus the value at I. That's a typo. That should be V, not U of S. Right, so in this case, in this picture here, I have a 0 and a 2 on the left side. The difference is 2, and that's the value on the edge. So the derivative is, you can think of this as a mapping from scalar functions on the vertices to scalar functions on the edges of a graph, or edges of the hypercube in this case, right? So this is a very standard way of thinking about derivatives in a sort of a discrete context here. Another useful notion will be a partial derivative, just like we like partial derivatives in the normal setting. A partial derivative on the hypercube would say, look, I will do the same derivative, but I only care, so if I want the partial derivative at I only care if I is the player I'm adding to the picture. If I'm not adding I, then I don't care. So just like with the regular partial derivative, I only look at changes, a partial derivative with respect to X, I only look at, when X is involved. Same thing here, I only look at the edges where I was involved in the transition. And it's not hard to see that because of the way the hypercube looks, the total derivative delta, the grad derivative here can be written as a sum of these partial derivatives as an operator. Okay. So far, so good. What next? So, and just a visual representation of this, that if you have a game, and remember it's a scalar function of the vertices, you can write out the overall derivative as the sum of these three derivatives. And it's not, again, this is not hard to work out. All these three things add together nicely. So what? So what is this very cool result by Stern and Tettenhorst? And I just recently discovered that this paper was part of Alexander Tettenhorst's senior undergrad thesis. So no pressure on anyone, but that's just crazy. I'm just mind boggled by that. What they did was they linked the idea of inessentiality, which I described earlier in purely sort of value function based terms, in a geometric language. Namely, they said that a game is an essential if and only if for all players I, you can express, if you write down the partial derivative of the game, it is the overall derivative of some modified game VI. Okay. So this may be a little hard to parse, but what this is saying is this: if I take a game and I take its partial derivative, right, with respect to I, so that basically means I'm looking at the differences on the hypercube edges of edges that involve adding I to the coalition, right? So it's like it's some sub-dimensional hypercube, And now I'm saying that I want that with just that and zeros everywhere else to be the overall derivative of some other value function. And if you start playing with this a little bit, you realize that since everything else is zero, right, and you only have edges along the contributions for I, the only way this is going to work for you is if all those contributions are the same. Otherwise, you won't be able to figure out values to put at the vertices of all the other nodes in the hypercube to make it work this way. Because the edge values are all zero. So you essentially are reintegrating back from the edges back to the vertices. The only way to make this work is if they're all the same. But if all those edge values are the same, that meant that I's contribution was independent of coalition. And so I was acting sort of independently of the rest. And therefore, all this is true for all of them. Therefore, the game is inessential. That's kind of the idea. And the other way is easy to prove. If the game is essential, then all this is trivially true. And this actually leads to another interesting observation, namely, I had said before that you cannot think of the Shapley value as coming from a projection. Right? It doesn't work to say that you find the closest inessential game to a given game and then look at the Shapley values of that game and that works. No. But it does work, sort of, if you work in the gradient space. In other words, the VI that you wanted, that witness, right, that gave you this property, if the game is not, right, already inessential, then the kind of VI you want to find is the one that is as close as possible to this ideal case. So again, let me repeat. If the game was inessential, in some sense ideal and good, you'd have this equality between grad VI and grad I of V. If you can't get that, if the game is not inessential, then it turns out if you find the VI that's kind of closest in this sense, right, to the grad I of V, the thing that satisfies the closest, something very miraculous happens. In particular, what happens is that these VIs have nice properties, and I'll write them all down here. And for those of you who have seen this before, all these properties basically look like the definition of the Shapley value. And so what this means, and this feels like a magician pulling a rabbit out of a hat, is that you can extract the Shapley values of V from the value functions I that you've produced. And I think, again, as always, it's better to think of this in terms of a picture. So let me walk through this. So we've talked about the first part of this picture. We took a value function V. It's a scalar function on the vertices, and we constructed the derivative space, right? All the different partial derivatives. And then I said, okay, this game is arbitrary. It may or may not be inessential. I don't know. But let me find these VIs, one for each player, defined by this argmin. So basically, look at the partial derivative grad 1V and find the closest vector in L2 norm to such that grad of that vector is close to this, right? And that's V1. Do the same for V2 and V3. Then what the property described on the previous page says is that if you look at the grand coalition value for V1, that will be Phi1, the Shapley value for V, for player 1 in V. If you look at the grand coalition value for V2, that's the Shapley value of player 2 in V. And if you look at the grand coalition for V3, that's a Shapley value of player 3 in V. So while the original idea of projecting onto a nice space of games and extracting Shapley values, that doesn't work, it sort of works the same way, but with these different games in this different projection space. What does this mean? What this means is that because we're doing this argmin, and we're doing this, what is now essentially an orthogonal projection, we now actually have a way to measure deviation from inessentiality. Remember that inessentiality was our ideal, right? If our game was inessential, then all the influences could be read off perfectly, everything made sense. If we don't have that, it's because there are interactions between variables, right? And so we can reveal that those interactions are happening by measuring the deviation from inessentiality. So remember, grad I of V and grad V of I are both maps to scalar functions over the edge space. You can think of them as vectors of length equal to the number of edges in the hypercube. So Ri, which is what we sort of propose looking at, is a vector over the set of edges that measures the deviation from inessentiality. So not a single number, but it's an entire vector. And the hope is that by looking at these RIs carefully, you can isolate when a single feature behaves additively with respect to model, or when a subset of features behaves additively with respect to model. In other words, can we decouple the interactions that might be going on in the model because of this? And so you can generalize this notion of essentiality. Instead of saying it's inessential in general, you can say the game is inessential relative to a particular set S if the contribution of S is independent of any coalition, right? So whenever you add S to a coalition that doesn't include any member of S, then everything works fine, right? And you can define the partial derivative with respect to S in a similar manner. And you can then show that essentially a game is an essential with respect to S. This is what we've shown in our work. If the sum of the residuals for each of the players in a set is 0. So remember, there's a vector sum. And so if it's not 0, the norm of this vector, and among other things, the norm of this vector measures the magnitude of the deviation from inessentiality, right? So how far it's gone away. And because these are all projections, notion of distance actually makes sense here in an L2 sense. Further, and this would not be interesting unless we could link it back to explanations. But here are things you can show. So, for example, and this is a very complicated lemma. So let me unpack it a little bit. What it's basically saying is that if I have a multivariate function, and I know that this function can be decomposed into a term that involves some variables and a term that involves some other variables, and they're disjoint, then in fact, if you compute the interventional value function as I described earlier, it will be relatively inessential with respect to set S in the sense that I just defined right now. Which means that if you compute the residuals, it'll tell you it's 0, and you'll know that this partitioning has happened. And you can do a similar result for this conditional expectation SHAP that I sort of described earlier. In other words, whichever method you use to look at explanations, residuals measure the degree to which interactions between your variables might still exist even after you found the Shapley values of features. Okay, almost done here. So just a quick sense of how to sort of think about these things. I'll walk through one very simple example. So this is one of these data sets where you want to essentially predict whether a room is occupied or not using basically time and the light conditions as a clue. It's obviously if it's daytime and it's lighted, or if it's nighttime and there's lights on, you might think. So in the first graph on the left, we have a plot of what the prediction will say that, for example, when the light is on and it's, during the daytime, you have a strong prediction that a room is occupied. And when it's outside the working hours or if it's dark, you have a low prediction. And the SHAP values are giving you the SHAP values of the feature light. And so what it's saying is that if you're in the middle of the day, light is sort of very influential in predicting whether you're going to, someone's going to be in the room or not. And otherwise it's not. Sorry. Yeah. Okay. Right. You can also look at the residual, right? So you can look at the residual of the light feature and say under which parts of the feature space does the light residual look large, which suggests there might be some weird interactions happening. And so what you see on the picture on the top right is that black being a larger value, you have this big core of dots right in the middle of the screen, which is basically saying for predictions of occupancy, the residual for light is high in the middle. And the reason, as it turns out, and we can look at this at the bottom figure as well, is that there's a strong interaction between the light feature and the time of day feature for points in that space, right? Because it depends exactly on what time of day it is. Right? Depending on the time of day, you're more likely to have, whether there's light or not, you're more likely to have someone occupying the room or not. And so that's where these features interact with the R. They don't interact with the R value all the time, but in this range they do. And this is where the residual tell you in this range you have to be more concerned about interactions than in other parts where there's less interactions. And you can do this in sort of other ways as well. We looked at sort of the adult data set, again, looked at interactions. Again, you can look at in these two graphs for looking basically at the, let me see. So the prediction of the income of the individual with conditioned on various features. It turns out that the residuals plotted on the y-axis here vary a lot more for women than for men, basically saying that for women, the prediction of income seems to be more tied to other features than it is for men. So what this does is basically go beyond what things like SHAP tell you, is to say, when might there be interactions that the Shapley value is not predicting for you? So just to sort of conclude, so Shapley values do capture the degree to which features act independently, and they do so in a kind of precise way in this projection sense that I mentioned. And residuals provide a measure of the limits of these Shapley-based explanations with regard to feature interactions. Other methods are trying to, like the Shapley-Taylor indices, are seeking to quantify these higher interactions in an axiomatic way. We think a geometric perspective is actually more interesting. And the reason we do is because in ongoing work that we're doing right now, we can actually connect this using the method that we've described. And in fact, we require the method that we've described to link the axiomatic discussion of Shapley values to Fourier-based analysis. So there's this big work in machine learning on how to do Fourier analysis of Boolean functions to understand issues of influence in models. And that so far, there's no way to sort of link that to work in Shapley values for technical reasons. But in fact, this connection that we described here, this geometric connection using the Stern and Tetterhorst work, actually allows us to do this. And for example, we can say something like this, that the Shapley value for a player I in a V is exactly what is the following. If you took the game itself and wrote it out as a polynomial, right, and in sort of the Fourier sense, then it corresponds to essentially a function of the coefficients in this polynomial of odd degree. So in particular, it contains a term for the player itself, but it also contains terms for coalitions of size 3, of size 5, by size 7 in complicated ways. And this in some way explains why the Shapley value by itself is not cleanly a measure of the contribution of player I. It's not even a measure of all the places where I shows up. It's the odd coalitions where I shows up, which is kind of weird. But this insight only comes once you do a Fourier analysis of the value function. So that's something we're doing in ongoing work to try and connect all these things up together. But there's a bunch of different works on Shapley uncertainty and the Shapley-Taylor indices that all seem to ultimately boil down to doing Fourier analysis, and we're trying to sort of nail all that down properly. So with that, I'll stop. I've been thinking at about 40 odd minutes, and I think this is a good time to take questions. And I just want to thank all my co-authors on both papers, Lizzie Kumar, my student, and my colleagues Cyril Friedler and Carla Scheidegger.
Awesome. Thank you so much for that great talk, Suresh, and thanks so much for taking the time to introduce SHAP in detail and providing the geometric perspective and so on. So Leaf has a question. He's asking, how does the info provided by residuals relate to that provided by SHAP interaction values?
So this is something we've been sort of exploring, right? So one way to think about this is this. The Shapley residuals, and I define them for players, but they can be defined for coalitions, are the things that are, so if you want to fully specify what's going on with the model, you need a full specification of all 2 to the D values for the D features. SHAP gives you D values. So there's stuff that's left behind. That's intuitively where the residuals come from, what's left over. But the residuals themselves apply to other coalitions as well. So if I give you, say, for example, all pairwise interactions, there's a residual that tells you what's left over after that. If I give you all triples, it gives you what's left over after that, right? So it's a way of saying, I can think of this as like saying, you do PCA or you do something else. You have the things that you can provide, and at whatever level of dimensionality you feel you can do it, and there's what's left. The residuals give you a sense of what's left and whether these things combine additively. So they're always relevant as long as you're not going to give me the full exponential set of things. But there's a more direct way in which we want to show how Shapley interaction indices, Shapley-Taylor indices, and all these things all work together. This is what I'm saying is a work in progress. It's a little bit tricky because of the Fourier analysis seems like a unifying theme, but they approach it in somewhat different ways, and it gets a little messy. So stay tuned.
So I had a question personally, because I think one of the recent works that we were thinking about was capturing the uncertainty in explanations, and the route that we took to sort of get there is basically the Bayesian route. And what if we come up with like Bayesian extensions of these models and so on, like limes and alignment SHAP, and we can go from there and capture some uncertainty. So I'm wondering, in the work that you are doing, does capturing uncertainty figure as one of the themes, and if so, how you're approaching that?
Yeah, that's a good question. And I will say that, I think what you're articulating is a much broader point, right? That there are, in the entire pipeline that goes from here's data to here's an explanation of the model, there are multiple stages of uncertainty. I think the stage of uncertainty you're referring to is, in my view, a different and important stage of uncertainty to the one that this paper is talking about. In particular, I would say that our uncertainty is really about uncertainty in the mathematical characterization of the game
Mm-hmm.
and its interpretation. So in other words, the minute you use
Mm-hmm.
the minute you use Shapley values,
Mm-hmm.
our concerns come into play.
Mm.
How you got there, whether you use Bayesian method or not, it doesn't matter.
Yeah.
But the Bayesian concerns speak to a different point of uncertainty in the process. So there's a whole sort of pipeline of these things. In fact, Sorel and her students have been sort of thinking very deeply about how these all fit together. And there are other forms of uncertainty. For example, I mean, the Shapley value estimation process, as I mentioned,
Right.
the exact computation of Shapley values is exponential time.
Right.
And so you have to, in the number of players. And so you have to estimate it somehow. So there are sampling-based methods. There are these more heuristic approximation methods like kernel Shapley. So they all introduce their own forms of uncertainty as well. Some of which are modelable, some of which are not. And so all of these factors play in. So these are, I think, different points of uncertainty in different parts of the process.
Right. And can you also comment a little bit on the scalability? Because I think, as you just referred to it, the computation of these values is computationally expensive. So, how
Yeah.
do we deal with that? And in general, I think, just as a broader point, so scalability in terms of explanation methods is not really something that has been hit upon in terms of literature as much as other aspects have been touched upon, right? Like their vulnerabilities and so on. So
Yes.
forth. So I'm curious what your thoughts are on that.
We have thoughts. We have that. So I mentioned sort of ongoing work on the Fourier analysis. We have ongoing work on the scalability as well. So first of all, one thing that I'll say right here is that I've been a little disappointed by is how people have not yet realized that there's actually a ton of work out there on doing Shapley value estimation at scale, which exists.
Yes.
And
Yeah.
sort of it was in a different literature, in a more algorithmic literature. Then the machine learning people, were doing this, and somehow they didn't connect up. And I think now people are beginning to realize the connections. So, for example, the framework that I described to think about Shapley values is this random walk, right? So
Yeah.
basically, what it's saying is do a random walk from 0 to n, and look at the contribution of value. Suggest an estimation scheme.
Mhm.
Do the random walk, do a number of trials, take the average, and hope your variance in your Chernoff bonds works out.
Mhm.
This works.
Mhm.
There are some increasingly sophisticated sampling methods. They basically work, and it's not based on the range of the value function. You can put it on your tail bounds and stuff, but basically that's all you need to do. So Shapley values are not that hard to estimate up to whatever degree of accuracy you want. You can make very precise bounds on these things by sampling. Okay. The problem is, of course, there are only n of those, but there are 2 to the n, 2 to the d
Right.
descriptions of residual. So we're in the process of so it turns out to be a bit more complicated. So we have to dig deep into the literature on sublinear algorithms. So this is why I put my algorithms hat back on as a theoretical computer scientist, and we draw on the literature on how to do sublinear estimation, basically saying, can I, somehow magically, without having to look at all 2 to the d components of the vector, estimate properties of the vector? And it turns out you can. I will say again, stay tuned on that. So we're working on that right now. But it requires understanding a lot more structure, and then it relies on this framework, this geometric framework. So that's the thing, it relies on the geometry that we've established from using the Stern and Tetraverse work. Without it, we wouldn't have been able to do it.
Right. Okay. So I'll take few audience questions now. So Emra has a question. Uh, Emra says, why can't I just apply a transformation to features to minimize their interdependence? Example, if they're jointly Gaussian, I can make them independent via simple linear transformation. If not, I can make it uncorrelated.
So the problem here is not that you want to remove the interactions. The problem is that you want to expose the interactions. So if you did something to remove the interactions, yes, you've removed them, but you've lost valuable information that you actually need. I actually want to know what the interactions are. I don't want to hide them, because I want to know if, for example, in the case of bias detection, right? I want to know if there are interacting variables where I'm seeing these influences that might actually constitute a form of bias. And there are many other debugging methods. So I want to reveal this and expose it, not hide it.
And Fabrizio asks, have you looked into coalitions that do not make sense given the data generation process?
So one line of work, which is sort of a more causal line of work, there's been some papers on this that basically say, look, let's build a causal model over our features. This corresponds to A, putting directions on the hypercube, and B, removing some edges of the hypercube, right? And let us now compute Shapley values on this graph, no longer a hypercube, in much the same way, looking at the average contribution along paths, blah, 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 blah. And there's been some success with that. Again, if you're within a causal framework and are willing to sort of buy into all the things that causal frameworks require you to buy into, you can go that way. So that's one way to address the idea of invalid coalitions. So that works in that context. I don't think that it's easy to do that in general. I will say that the mathematics of what we're describing get a bit more hairy, mainly because while the derivatives and everything all makes sense, everything works, because you don't have the hypercube, you no longer have the fact that essentially the second derivative looks like the Laplacian, and then good things don't happen. So the mathematics starts getting a little bit more messy, but it can be done. In fact, even in Stern and Tetterhorst's original paper, they explored how to sort of build up the geometry in the case when you have weights, when you have some edges missing, and so on. So the mathematics doesn't work. Some of the things that we said we can do will be harder to do in that case as well.
Right, got it. And Martin asked that he had basically read that SHAP values handled correlation between variables better than other feature importance measures. So is it a lost cause to hope that there is a measure of feature importance that is actually fully robust to feature correlations?
That's a great question. I don't know the answer. We have been struggling for now, I would say about a year and a half, to try and figure out if there, given all the problems we've been seeing with all the different, I think they all have problems. Is there a one true thing? And I'm beginning to wonder if there is one or not. I don't know anymore. I don't know, Hima, what you think about this, but the quest for one is tantalizing. Right. But maybe we're going along the wrong path by trying to find one single thing, and maybe we need to really look at use cases more carefully and try to understand. So, for example, one thing that I've been interested in with all my colleagues is that if we look at the narrow question of discrimination, right, which is not the only reason you want explanations, but is one important use case, right, your discrimination against groups and all, then the kind of explanation you need there involves determining things like indirect influence, right? What is the indirect influence that race may have an outcome, even if it's not an explicit part of the process? And it seems like the kind of feature importance thing you might need might look a bit different from what you might need for something else. So I don't yet understand how to break down the use cases. So, I mean, yeah, Hima, what do you think? What do you think we should be doing here?
Yeah, no, I think it's also a question that I have often pondered on, but I agree with you that I think you used a word that the search for that is tantalizing, but we just don't know if we are hitting the right tracks. I think that completely just sums up my views on this question for sure. But yeah, no, I think that is something to be thought more about. So maybe I'll just there are a bunch of other questions, but in the interest of time, maybe I'll just wrap up with the last one. And the rest of you who have submitted questions, we'll just share these offline with Suresh, and hopefully he can try and answer on the Twitter forum and so on. So the last question that I'm going to take is Aditya asked, if there are greater than two features interacting with one particular feature, will SHAP residuals be able to inform the magnitudes of individual interactions?
So are you saying that I have feature 1 and then features 2 and 3, and then 2 and 1 are interacting and 3 and 1 are interacting, and I want to understand these things?
Yeah, right.
Yeah, so I think, so you can define, so the short answer is yes, you could look at the residuals R12 and R13 and R23 and look at them. I will say that we're still trying to figure out exactly how those tease apart. And again, like I said, this is why I think we've been trying to go back to the Fourier analysis. So one way to think about this is that if you write down the value function of a game and take its Fourier transform, what you end up with is a representation in terms of a multilinear polynomial, where each of the terms in the polynomial is basically a coalition of vertices. So basically like sum of a1 x1 plus a2 x2 plus a2 x3 plus a12 x1 x2 plus a13 x1 x3 and so on, right? And so once you have that Fourier representation, you can start reading off coefficients that tell you, in some sense, the magnitude of the coalition term right there. Mm-hmm. And so we are able to express residuals in terms of those coalitions, at least for single players. We're still trying to figure out what it means for these combination coalition things. But we do believe that the Fourier analysis is the way to go to figure this out.
Okay, awesome. Thank you so much again, Suresh, for answering all these questions. And again, there are a bunch of other audience questions, but we'll send that to you over email in the
So
interest of.
one thing I didn't understand is the second half of your participant discussion. Is that something I'm invited to or not? I don't know how this works. So because
It,
maybe there's a place, because I know you talked about other questions about, going into research
right,
and stuff.
yeah.
I don't know
So
if
we
that's a
just
place
want
for
to,
that.
yes, so we just want to get into those now, where we
Okay.
can
Okay.
like
Good.
deep into your research process
Yep.
and how you think about it. And
Yep.
after that, there'll be participant discussion. You are welcome to stay for that, by the way.
Okay.
It's
Okay.
optional, but if you want to, you're welcome to stay for that.
Sounds good.
So let me jump right into the journey questions now that we are done with all our Q&A for the talk and so on. So let me start by asking you to describe your journey a little bit. So what motivated you to even consider research as a career? How did all this start?
So the only defining characteristic of my research journey was that it was not planned. And every step of the way, I made some local decision that led me somewhere, and then it led me somewhere else. So in particular, right? I mean, I kind of knew I wanted to do computer science. That was fine. So I went and did it for an undergrad degree. I kind of got the sense that I should probably do a PhD, although I really, frankly, had no idea what it meant to do a PhD. I think in retrospect, I had no clue at all, but I thought I did. So I came and did my PhD. I thought I wanted to do either structural complexity theory, which is a very esoteric subset of complexity theory, or AI, and I didn't know what that meant. So when I came to grad school and reached out to one professor who was doing something in AI, and they basically said, "Here's a proceedings of the latest conference. Go read it." That scared the heck out of me, and so I went and I ended up running away from that and going back into algorithms and doing algorithms and geometry for my PhD. I didn't know anything about computational geometry till I hit it in my PhD, and so it was kind of funny that I got into it. And that's been kind of my characteristic over the years. I've just sort of found I've been curious about things. And once I got curious about something, I would dig into it and I would dig and dig and dig and dig and dig. And then something interesting would come out of it. And I would do that for a bit. And then I would find something else. And so that led me, I went from doing computational geometry to fooling with GPUs before they were cool. And then, right, like trying to build models for how to do GPU computation before any of the stuff that we see now has happened. Then going into information theory and thinking about information theory for data analysis, which led me sort of through various byways into clustering. And I was never really into machine learning till one of my students basically dragged me into it because they wanted to do machine learning and they didn't care that I was asking them to do something else. And they said, "Well, I'm not going to do what you're telling me to do. I want to do machine learning." I said, "Okay, fine. You got to teach me machine learning then." So they essentially taught me machine learning. And that's been the case for every one of my projects since then. In fact, this whole work on explainability, I'd spent like 3 years trying to run away from any questions of explainability till my student Lizzie basically insisted that we sort of think about this because she was annoyed about something. And I think most of my papers are written because I'm annoyed about something or pissed about something, and I have to sort of write a paper to clear my mind. And that's how I got into explanations. I mean, the whole area of fairness, though, that was a little bit more planned in the sense that I was doing a sabbatical and thinking about what I want to do next. And I was kind of bored of writing yet another clustering paper or data mining paper or whatever. And I thought I want to think about what the world would look like after we finish writing all those papers. Ha. But anyway, so I imagine that, once you the questions of verifiability and trustworthiness came up then, and that got me thinking, and then one thing led to another, and here I am now.
So, so I know that this is something that often comes up, and a lot of the folks who attend these seminars are also PhD students, and they often ponder this question. So, why did you consider a career in academia versus, say, research in industry or something else? Like, what made you make this decision?
So I've done both, right? So when I came out of grad school, I had options to go to academia or industry, and then after a lot of sort of agonizing, maybe more than I should have, I went to industry. And I went there thinking eventually I'll get back to academia, but eventually became longer than I expected. But I eventually did come back to academia. And I think okay, I would say that my answer prior to, I don't know, November of 2020 will be very different to my answer now.
Oh,
Having said that, I think, there are challenges, I think, to working in any environment. Academia tends to provide a certain illusion of freedom. I say illusion because it's not totally false, but it's not as if you can do whatever you want. You still have to somehow justify it, argue that someone should pay you money to do that, and so on. So it's not, it's not like do what you want and no one cares. You have to make people care. You have to write papers, you have to get grants, and so on. In industry, you have a much more chance to sort of have a certain kind of impact, not impact in general, but a certain kind of impact in terms of productizing, sort of deploying, doing the technology transfer. That would be harder to do in academia. It's a different set of questions. It's a different time horizon. It's much more fast moving.
mhm.
Now, since November, of course, I've had to question a lot of what I said about this because I think we are seeing problems, frankly, with how folks in industry are able to do their work freely and without being muzzled in many ways. I don't need to tell you all about what happened at Google, and I'm pretty sure this is happening other places as well. So that's a question. I think it's a hard question for people to answer, and it's tough. But I think if I think the answer is different for everyone. Everyone has to come up to their own path for, and they're all valid answers. Okay, it's not for me to say what people should do. You go to a nonprofit, go to the ACLU, go to a teaching college, go to academia, go to industry. It doesn't matter. The point is to find a path that's sort of harmonious with what you enjoy. If you enjoy doing things in a certain way, then if you enjoy sort of the deployment, if you enjoy sort of seeing impact in software, maybe a certain kinds of industry jobs are good for you. Maybe there are other kinds of academic jobs that are good for you. It depends. I think there are many options. I think in computer science, we're lucky that we have these options. In a lot of other fields, there really only one choice. You go to academia, or you do nothing, and that's very hard. We have many options, so try some out, right? I mean, I was in industry for a few years. I went to academia after that. I mean, I'm not saying these things are easy, but you do have the options to try some out and do internships, do other stuff. You'll get a sense of what it's like.
Yeah, that's definitely true. I think I echo the sentiments that I think as computer scientists we are probably more privileged than some of the other branches because there are multiple career paths that we can take and still continue to be active in research to varying degrees, of course. But yeah. And do you have any thoughts on the future of trustworthy ML? Say, if we were to look forward for like 2 to 5 years, do you still think this would be a very relevant research area? And do you see yourself personally working on the kinds of problems that you're working on in like explainability and fairness?
So I have been right about a prediction once in my life. I'm not going to try to be right a second time. So I don't know if I can make predictions about the field. So, but I'll answer the second part. I think this is a fascinating area, and I think we have only begun to scratch the surface of the huge implications of this relentless, inexorable move towards an algorithmic society. I do not think we have fully reckoned with the consequences, good and bad. I do not think we have reckoned with how it's going to change how we think about our role in society, our role as people, what it means to be human. There's a lot of things that are going to need to be unpacked. Not all of them are technical things, but they're going to be technology adjacent. And I will say that this is my personal thing, right? Is that as computer scientists, we are extremely adept with the technical exposition of what we do. And we tend to shy away a little bit from trying to draw more broader meanings of the work we do. I think we have more to offer than we think we do. I think we have more to offer in terms of how computation itself and the language of computation says things about the world. In that sense, we're not that far from economics, where the language of markets and players and interactions tends to be able in some ways to speak to how people interact, in limited ways, of course. I think we have that ability to do that as well. And I think we should be more free, more willing to embrace that opportunity to use our insights from computer science and computation to speak to how this is going to affect the world, because we're building the technology that's going to affect it, and we should know that.
Right.
And no one else can do that.
Yeah, no, that's a great point. And I guess the last question in the interest of time again. So do you have any advice to younger researchers, students, even for new assistant professors and so on, as to how do you think about picking problems that are likely to be impactful? So what is your process? What advice do you have for other junior researchers in the field?
So I'll tell you my process, because I don't give advice because everyone's different, and I don't know enough to be able to say this is what you should do. All I can say is this is what I've done, and it has worked for me to some degree because of who I am. I tend to be extremely curious. I tend to ignore disciplinary boundaries, which means I have to kind of often spend a lot of time reading stuff I have absolutely no clue about, and hope that eventually I can figure out things. I was writing a paper once for which I spent essentially 2 years teaching myself differential geometry and Lie algebras and Lie groups and stuff like that. I don't know why I did it, but I did it because it was just fascinating to me and I felt like I needed to do it. And I ended up writing 2 papers. I don't think I've ever written a paper since, but that stuff is in my head and I'm happy. So I'm happiest when I'm exploring a brand new area like this. I mean, this paper that I was referring to here in the talk, it uses Hodge theory, something I've never fully understood. Luckily, the actual mathematics is much simpler, but you had to get through the Hodge theory and pull it out and realize it wasn't necessary to figure out what was going on. For me, I have always enjoyed doing that, whether it's in pure math or whether it's in the social sciences, reading more about, say, critical race theory or reading more about microeconomics and all. I found that curiosity be helpful to me to make me happy. It has also meant I've often been on the fringes of what's core to a field because I'm always looking for the new stuff. That's a price. I haven't, I wouldn't say I paid a price, but the things that I'm not in the core of field, it's because I've done that. And I think the truth is if you go with what you enjoy and what makes you really happy, no matter what the impact is, you'll have felt some joy along the way because impact is not up to you. Impact is a function of luck and circumstances. I got lucky that I jumped into an area that suddenly became big. I'm not claiming any credit for that, right? But I got lucky. And so it may not have happened, but as long as I enjoyed doing it, it was going to be okay. I was happy doing the stuff I was doing. So I think for me, that seems to work best, that I do something I really enjoy and I can find some happiness in the process. And the impact will happen when it happens. It's not up to me.
Awesome. Thank you so much once again, Suresh, for joining us and sharing all the tidbits of wisdom and for going over your work in such detail. Really love the presentation. Thanks again for.
Thank you all for questions and for listening. And thank you, the Trustworthy ML folks, for hosting me.